Hello. In continuation of alkali metals, we'll go with now extraction of sodium. Sodium extraction is discussed under metallurgy category. Here I give you just a brief intro. Sodium can be extracted by the molten sodium hydroxide electrolysis. This method is called Castner's process, where the products are at cathode sodium and at anode oxygen. Downs method is cheap method. In Downs method, we use molten sodium chloride, in which you are going to get sodium at cathode and chlorine at anode. This is Downs method, one cheap method, and Downs method is best. Downs method is most used. Sodium properties all we have covered in the general properties. The same properties will be there. In the compounds of sodium, the first important compound is sodium hydroxide, which we call as caustic soda, because when it falls on the skin, it makes the protein part as pulp. That's why it is called caustic soda, sodium hydroxide. Potassium hydroxide is called caustic potash. Sodium hydroxide is caustic soda. The preparation methods are, the first one is gaussage process, or you say causticization process. It is sodium carbonate reaction with calcium hydroxide. When sodium carbonate reacts with calcium hydroxide, it forms sodium hydroxide. This is laboratory technique, gaussage process. Another one is Loic process. In Loic process, we are going to treat iron oxide with sodium carbonate, so that you will get sodium ferrate. The sodium ferrate, when treated with again water, you will be getting sodium hydroxide. The most important one is Nelson's process, or you can use Kastner-Kellner process or Kellner-Salve process. In all these methods, we are going to use brine solution. Brine solution is sodium chloride aqueous solution. We are going for electrolysis of brine solution. The electrolysis reactions are NaCl aqueous solution will give you Na plus ions, Cl minus ions, H plus ions, and OH minus ions. Cl minus ions will go to anode, gain electrons, and turn into chlorine. This is the reaction. H plus ions go to cathode, gain electron, and become hydrogen gas. So at cathode, hydrogen gas, at anode, chlorine gas, and in the cell, sodium hydroxide is formed, Na plus OH minus. This is the overall reaction. So Nelson's process or Kastner-Kellner process or Kellner-Salve process, the technique is going to be same. And finally, to prevent the reaction between the products, porous diaphragm is used, because the chlorine formed in the reaction will again react with sodium hydroxide. That must be prevented. When H plus and Na plus are there, why H plus is discharged at cathode? For that, the reasons are discharge potentials. You can see the discharge potentials. One important observation is, in Kastner-Kellner process, we use mercury as the electrode. Here, in Kastner-Kellner process, we use a rectangular tank which is divided into three compartments: outer compartments and inner compartment. Two outer compartments and inner compartment all will be having mercury at bottom. The mercury at bottom in outer compartments works as cathode, and in the inner compartment it is anode. This is due to induction. In the outer compartment, as it is cathode, it reacts with sodium plus ions to form sodium amalgam. It is providing electrons, it is functioning like cathode. But in the inner compartment, the same sodium amalgam, the reverse reaction is possible now. It gives you sodium plus ions. One very interesting method this is. So in outer compartment, graphite will be anode, which gives you chlorine gas. In the inner compartment, iron rods will be cathode, which gives you hydrogen gas. And in the cell, you are going to get sodium hydroxide. The technique is same reaction, but the only difference is, if you are using mercury as cathode, then the method is called Kastner-Kellner process. That is also called mercury cathode method. Then coming to the physical properties of sodium hydroxide. Sodium hydroxide is white crystalline solid, hygroscopic, soapy to touch. As I told you, it is called caustic soda because it converts the skin protein into pasty mass. Coming to the chemical properties, sodium hydroxide in the air it reacts with carbon dioxide to form sodium carbonate. With acids HCl, H2SO4, any acid you take, sodium hydroxide is strong, so it reacts. Acidic oxide, sodium hydroxide, reacts with carbon dioxide type of compounds or sulfur dioxide or sulfur trioxide, you can say, nitrogen dioxide, all these. And salts are formed. With carbon dioxide, sodium carbonate, sulfur dioxide, sodium sulfide, sulfur trioxide, sodium sulfate. With nitrogen dioxide, interestingly, you will get here NaNO2, NaNO3. Look at this reaction. Okay. The oxidation state of nitrogen in NO2 is +4. NaNO2, the nitrogen oxidation state is +3. NaNO3, oxidation state is +5. We don't have any salt of sodium and nitrate with +4. That means NO2 is a mixed oxide of actually HNO2 and HNO3, so you are getting here both. One interesting reaction. Then we are discussing about sodium hydroxide, its reaction with amphoteric oxides. Sodium hydroxide reacts with Al2O3 to form sodium metaluminate, and generally we say when this is dilute sodium metaluminate, if we are taking sodium hydroxide little concentrated, it will be sodium aluminate also. Sodium hydroxide with zinc oxide, sodium zincate. Sodium hydroxide with tin oxide, sodium stannite. Sodium hydroxide with SnO2, tin dioxide, that is sodium stannate. See the difference, SnO stannite, SnO2 stannate. It is +2 oxidation state. In Na2SnO2 also +2 oxidation state. In SnO2 +4 oxidation state for tin, here also +4. Similar type of reactions you can see here. PbO, sodium plumbite, PbO2, sodium plumbate. Have a look at these reactions. Very similar to stannous oxide, stannic oxide, lead monoxide, lead dioxide. With non-metals, very interesting reactions are there. Sodium hydroxide reacts with boron to form Na3BO3, sodium borate. With silicon, Na2SiO3. Na2SiO3 is sodium silicate, which is called as water glass. In these reactions, hydrogen gas is released with boron and with silicon. With phosphorus, this is called a disproportionation reaction. The oxidation state of P4 is 0 and the oxidation state of phosphorus in NaH2PO2 is +1 and pH3 is -3. Sodium hypophosphate and phosphine are formed. This is a disproportionation reaction. Oxidation state of same atom is changing into two different oxidation states. The same reaction you can expect in sulfur case also. Sulfur with sodium hydroxide forms sulfide and sodium thiosulfate, which we call hypo. Na2S2O3, 5H2O is called a hypo. Here also same case, the disproportionation reaction takes place. With halogens, there is a difference from chlorine, bromine, iodine to fluorine. Fluorine reacts with sodium hydroxide in a different manner. Cold and dilute sodium hydroxide with fluorine gives OF2, oxygen difluoride, whereas hot and concentrated sodium hydroxide gives O2. Cold dilute OF2, hot concentrated O2. Chlorine, bromine, iodine, all they react in same way. These reactions are disproportionation reactions. With cold and dilute, NaCl, NaOCl. Oxidation states you see -1 and +1. Hot and concentrated, NaCl, NaClO3, -1 and +5. Bromine and iodine also same case. Sodium hypochlorite, sodium chlorate. With the cold and dilute, sodium hypochlorite. With hot and concentrated, sodium chlorate. See carefully, these are important reactions. Repeatedly asked in exams. Then reaction with salts, interesting these are. See, with iron chloride and manganese sulfate type of salts, it forms precipitate. For example, FeCl3. FeOH taken thrice. This is reddish brown type of precipitate, which is insoluble precipitate. Manganese hydroxide, a white color PPT, insoluble. Sodium hydroxide with salts we are discussing, ferric chloride and manganese sulfate, insoluble precipitations are found. But aluminium chloride and zinc sulfate type of salts, if you see, aluminium hydroxide is found, which is a white PPT, but if you are adding excess NaOH, it will be dissolved. Same case with zinc, zinc hydroxide, white precipitate with excess NaOH, it is again soluble due to the formation of Na2ZNO2. Similar, you can expect in chromium chloride also, chromium hydroxide, green precipitate with excess of NaOH, Na2CrO4, sodium chromate, yellow solution, pale yellow solution. So NaAlO2 in aluminum case, Na2ZNO2 in zinc case, Na2CrO4 in chromium case, soluble. Okay, now first precipitation is formed, then that is soluble in excess of NaOH. You will get these in qualitative analysis also. Then some unstable hydroxides. You see mercury chloride gives you mercury hydroxide, which is unstable, gives you mercury oxide, HgO. And one important ammonium test is, okay, now whenever if you want to go for qualitative analysis of inorganic salts, if ammonium cation test if you want to do, take the salt in your palm, add 1 drop of sodium hydroxide, rub it and smell it. If the smell is pungent, if you are getting pungent odor, that is nothing but ammonia, and that is this reaction. Sodium hydroxide with NH4Cl, ammonia gas is released. Okay, just to warm it, you will get ammonia. So these are important reactions of sodium hydroxide. We will have a look at sodium carbonate. Sodium carbonate formula is Na2CO3, anhydrous amorphous powder. Na2CO3 is called soda ash. Hydrated salt Na2CO3 NH2O is washing soda. Preparation, Leblanc process. Raw materials are sodium chloride, H2SO4, CaCO3 and coke. Nowadays these are asked in exams. What happens? NaCl reacts with H2SO4 to form salt cake, sodium sulfate. This sodium sulfate reacts with calcium carbonate and coke powder to form black ash. Black ash is a combination of Na2CO3 and CaS. Na2CO3, CaS is called black ash, which is further hydrolyzed to get Na2CO3, and calcium sulfide is precipitated, sodium carbonate. Another method is one very important method for JEE type of exams or NEET exam also, you can say Salvage method, which is called as ammonia soda process also. The raw materials are ammonia, calcium carbonate, brine solution, and actually carbon dioxide is required here. Though calcium carbonate is heated to get carbon dioxide, there are 3 towers we generally use in this one. The first one is ammonia saturated tower. In this, brine solution gets saturated by ammonia gas. What happens here? Brine solution, when that is mixed with ammonia, then the same combination is sent into carbonation tower, where the reaction takes place like this. Ammonia, water, carbon dioxide to form ammonium bicarbonate. Brine solution gets saturated, we said, na? So sodium chloride is the brine solution which reacts with this ammonium bicarbonate to form sodium bicarbonate, NaHCO3. This NaHCO3 further heated to get Na2CO3, sodium carbonate. Very simple technique. Ammonia, water, carbon dioxide to fetch ammonium bicarbonate. In some books they will give you ammonium carbonate, further ammonium bicarbonate. You can write anyway. However, it is going to form ammonium bicarbonate. When reacts with NaCl, it forms sodium bicarbonate. Then sodium bicarbonate will give you sodium carbonate on heating. So in calcination tower, the reactions, as I told you, carbon dioxide is obtained from calcium carbonate. On heating, you will get carbon dioxide. This calcium oxide again treated with water to form calcium hydroxide. In ammonia regeneration tower, this calcium hydroxide is used because whatever the ammonium chloride is formed, that reacts with calcium hydroxide to form ammonia gas. This ammonia is useful in our first step. Okay, ammonia reacts with water and carbon dioxide. For that purpose, you can use this. That means the carbon dioxide and the ammonia are going to be reused in this method. This is one important technique. The question they will ask you about this is, in this method you cannot prepare potassium carbonate because actually we get here sodium bicarbonate. The sodium bicarbonate is heated here to get sodium carbonate. The same technique you cannot apply for potassium because potassium bicarbonate is too soluble in water. You won't get potassium bicarbonate solid so that you can heat it and you can get potassium carbonate. So potassium carbonate cannot be prepared by Solvay's method. Solvay's method exclusively for sodium carbonate. Then some properties. Even you can prepare the same sodium carbonate by Nelson's process. In Nelson's process, we are going to prepare sodium hydroxide. In between, you need to send carbon dioxide. As we know, carbon dioxide can react with sodium hydroxide and form sodium carbonate. So some properties we have seen. Na2CO3, as basic in nature, can react with acids. So you can see here, with HCl, NaCl is formed. Sodium carbonate further can react with carbon dioxide to form sodium bicarbonate. This is one important reaction. Na2CO3 plus CO2 plus H2O, sodium bicarbonate is formed. So this reaction we are going to discuss in the preparation of sodium bicarbonate. Then with silica, Na2SiO3, with sulfur dioxide, Na2SO3, but excess of sulfur if you are using Na2S2O3, sodium thiosulfate. Sodium carbonate when treated with calcium chloride, CaCO3, precipitated with magnesium bicarbonate, sodium bicarbonate and magnesium carbonate. So these reactions you can see actually in the removal of hardness of water we use. Calcium chloride and magnesium bicarbonate type of salts actually cause hardness to water. So water hardness, temporary or permanent, both can be removed by sodium carbonate. These are the reactions in that. Then sodium carbonate reacts with barium sulfate to form barium carbonate, that is Na2SO4 extra compound. Then sodium bicarbonate is NaHCO3. As we were discussing, it is prepared by the same technique. In the ammonia soda process, you stop at that place where first sodium bicarbonate is only formed, which is on heating you sodium carbonate. Otherwise, add little CO2 and water to sodium carbonate, that forms NaHCO3. Preparations, ammonia soda process, as I was saying, you can stop at this place because on further heating of this NaHCO3 you will get Na2CO3. This I was saying you, K2CO3 cannot be prepared. Reason, KHCO3 is too soluble that it cannot be solidified. Na2CO3 plus H2O plus CO2, NaHCO3, as we were discussing just now. Uses, it is used as antacid and as baking soda and baking powder. Here I didn't mention, but I will tell you one thing about hypo and microcosmic salt and potassium. We will discuss in another video. I'll just give you one line about this sodium carbonate and sodium bicarbonate. Compared to sodium bicarbonate, sodium carbonate is strong base, and you will be asked about a question related to phenolphthalein and methyl orange. Phenolphthalein gives color with only strong bases, so you can expect with sodium carbonate, not with bicarbonate. But methyl orange you can expect with both sodium carbonate as well as sodium bicarbonate. So remember, methyl orange gives yellow colored solution with both sodium carbonate and sodium bicarbonate, but phenolphthalein gives only with sodium carbonate, pink colored solution with sodium carbonate only. So to distinguish these two, sodium carbonate and sodium bicarbonate, phenolphthalein should be used, not methyl orange. Okay, this is one point. Then sodium carbonate is not having any hydrogen, but sodium bicarbonate is having one hydrogen. So this is called actually acidic salt. This cannot be stored along with any base because it can react. Sodium carbonate can be stored along with any base because there is no reaction between them. But sodium bicarbonate is having one acidic hydrogen, so it cannot be stored with any base. The hydrogen part of this will react with that one. Okay, we'll discuss